It begins with a simple question that echoes across every era of human curiosity. How does the world change when an idea first arrives as a whisper, dismissed as error, and only later becomes the foundation of everything we know? History is full of these moments, quiet revolutions launched by people who saw something others refused to see. Some worked in crowded laboratories, others in distant fields or observatories, and a few simply followed a puzzle that refused to let them go. Their stories form a constellation of discovery shaped not by triumph alone, but by doubt, resistance, and the patience required to challenge accepted truth. This is the story of ideas that were once laughed at, ignored, or condemned, only to reshape the modern world. You can picture the scene again and again. A solitary figure standing before the established order, offering an interpretation that feels too strange to accept. A meteorologist suggesting continents once wandered across the planet. A priest proposing the universe had a beginning. A chemist claiming invisible organisms were responsible for illness. A young doctor observing that something as ordinary as washing hands could save countless lives. In each case, the reaction from their peers was remarkably similar. Skepticism hardened into ridicule. Professional laughter echoed through lecture halls. Some faced public scorn, others faced exile, isolation, or worse, yet their ideas endured. They persisted not because of charisma or force of argument, but because nature, in the end, does not lie. Evidence builds, slowly and quietly, until the truth becomes undeniable. At the core of these stories is something deeply human, the tension between what feels comfortable and what proves to be real. Every era imagines itself as enlightened, believing it finally understands the rules of the universe. And in every era, there are discoveries that reveal how limited that confidence truly is. The world is wider, stranger, and more intricate than any generation assumes. Theories once labeled foolish now guide spacecraft, inform medicine, and shape our understanding of the cosmos. What was once unthinkable becomes obvious. What was once mocked becomes essential. This opening chapter invites us to step into that space between belief and discovery. To imagine the world as it was before these revelations took root, before tectonic plates moved, before germs existed, before rocks fell from the sky, before the universe expanded, before a forgotten city emerged from the soil, before invisible matter outweighed the stars, before a simple act of hygiene saved millions, before a protein could replicate without a strand of DNA. In each case, the impossible eventually became the ordinary. So what do these stories tell us? Perhaps they remind us that truth rarely arrives with fanfare. It often starts as a faint observation, a stubborn question, or a pattern that refuses to be ignored. It grows slowly, shaped by the perseverance of those who are willing to look again when everyone else looks away. And it challenges us to recognize that certainty is fragile, that knowledge is a moving frontier, and that even now our understanding of the world is incomplete. As we begin this 14-part journey, we enter a landscape shaped by tension between old ideas and new evidence, between tradition and inquiry, between what we believe and what we have yet to learn. These stories are not just about science. They are about courage, patience, and the enduring human desire to understand. They ask us to consider a final question as we step forward. What ideas today, still ridiculed or ignored, might one day define the world we have yet to imagine? It started with a puzzle no one else cared to solve. Why did the jagged edges of South America seem to fit so perfectly against Africa, like pieces of a torn map? In 1912, a German meteorologist named Alfred Wegener stood before a room of distinguished geologists and dared to ask that question. His proposal was simple, even poetic. What if the continents were once joined, a single ancient landmass torn apart by time? He called this supercontinent Pangaea, and he believed the continents drifted apart like icebergs floating across a vast sea. The reaction was not polite disagreement. It was ridicule. Wegener wasn't a geologist. He studied weather and ice. To the establishment, he was an outsider, with no place speaking about the deep mechanics of Earth. His theory of continental drift was met with open contempt. Critics scoffed at his evidence, even though it was compelling. Fossil records that matched across oceans, ancient glacial scars found in deserts, and coastlines that aligned with uncanny precision. But he lacked one thing: a mechanism. How exactly could continents move? Without that answer, he was dismissed as imaginative but unscientific. Wegener died in 1930 during an expedition to Greenland. His theory considered a failure, his name attached to folly. Yet beneath the ocean's surface, a quiet revolution was brewing. In the 1950s and 60s, Cold War submarines mapped the ocean floor, searching not for scientific truth, but strategic advantage. What they found was startling: a massive undersea ridge stretching down the Atlantic, and patterns in the seafloor that showed it was spreading outward. Bands of magnetic rock, perfectly symmetrical on either side, revealed that the crust was forming, moving, changing. This was the missing piece Wegener never had. The continents were not bulldozing through solid rock. They were riding on enormous tectonic plates, drifting atop a restless mantle powered by heat deep within the Earth. By the time the textbooks caught up, Wegener's drift had become the cornerstone of a new geological gospel: plate tectonics. The theory now underpins everything from mountain formation to earthquake prediction. Looking back, the transformation seems inevitable, but in the moment, it required someone willing to be wrong in public, to endure decades of scorn for seeing what others refused to consider. Wegener's story is not just about geology. It's about the cost of being first. And what do we do with that kind of legacy? We rewrite the textbooks, yes, but we often forget the laughter, the dismissal, the years spent in the cold. We like our heroes polished, vindicated, and posthumously correct. But progress rarely arrives without friction. It's uncomfortable. It asks us to trust a pattern before we understand its cause. There's something deeply human in Wegener's story. A reminder that sometimes the truth isn't loud or obvious. It's slow, inconvenient, and born in the margins. And the next time someone points out a pattern we've overlooked, we might remember that the ground beneath our feet was once considered motionless. So we end with a question: how many ideas have we silenced, not because they were wrong, but because they came from unexpected voices, asking questions we weren't yet ready to hear? What if the Earth wasn't the center of everything? That question, now a footnote in school books, once carried the weight of heresy. For over 1,000 years, the geocentric model, Earth at the center, stars and planets in divine orbit, was not merely a scientific belief. It was a sacred truth, rooted in philosophy, theology, and the human desire for cosmic importance. To question it was to risk more than ridicule. It was to risk damnation. In the quiet study of a Polish cathedral, a canon named Nicholas Copernicus worked slowly, meticulously, sketching a different vision. In his model, the sun, not the earth, sat at the center of the universe. It explained the strange, looping paths of the planets with elegance, but it also dethroned humanity from the celestial spotlight. For years, he kept his theory hidden. Only when death approached did he allow it to be published. And even then, the world barely noticed. The man who refused to stay quiet was Galileo Galilei. If Copernicus whispered, Galileo roared. Armed with a telescope, newly crafted, rough but powerful, he peered into the heavens and found them flawed. Mountains on the moon, sunspots on the sun, moons orbiting Jupiter, and most damning of all, Venus showing phases, proof it orbited the sun, not Earth. These were not metaphors, they were direct observations. Galileo didn't write in Latin for scholars. He wrote in Italian for everyone. He argued with wit, clarity, and fire, and the fire answered back. The Catholic Church, fearing the implications, summoned him to stand trial. He recanted under threat of torture. Legend says he muttered, "And yet it moves," as he left the court. Whether he said it or not, the world remembered the defiance. He spent his final years under house arrest, his books banned, his voice silenced. But the stars did not change. The observations could not be unseen. A century later, Newton would provide the laws that explained it all. How gravity held the planets in orbit, how the universe moved not around us, but as part of a grander system. It would take until 1992 for the Catholic Church to formally admit its error. Nearly 360 years after the trial, the apology came, not with fire, but with humility. Galileo had been right. The earth moved. This chapter is not just about astronomy. It's about what happens when power meets truth. Galileo's telescope showed the heavens were not perfect. But what terrified the authorities was not the craters or the moons. It was the idea that knowledge could come from a lens rather than a scripture. We like to believe that reason always triumphs, but in reality it often waits. It endures silence, persecution, even exile. And when it returns, it does so not with vengeance, but with clarity. So here's the question that lingers like a faint star in the sky. In our time, what truths are we resisting? Not because they lack evidence, but because they unsettle our place in the universe. Imagine a world where hospitals were more dangerous than the diseases they tried to treat, where doctors moved from dissecting corpses to delivering babies without washing their hands, where infection was a mystery and death in childbirth was so common it was considered inevitable. This was medicine in the mid-19th century, a time of brilliant ignorance. Into this world stepped a man not trained in healing, but in chemistry, Louis Pasteur. He wasn't searching for medical miracles. He was trying to save French wine. Some batches would spoil mysteriously, turning sour despite careful storage. Through a microscope, Pasteur saw what others had missed: tiny living organisms, multiplying unseen. He realized these microbes weren't just spoiling wine. They could be spoiling the human body. It was a breathtaking leap. If microorganisms caused fermentation, could they also cause disease? The medical establishment scoffed. The idea of invisible creatures attacking the body seemed like superstition. Besides, doctors were gentlemen. The notion that they carried death on their own hands was not just absurd, it was offensive. Undeterred, Pasteur staged dramatic public experiments. His swan-necked flask, filled with sterilized broth, remained clear for weeks unless exposed to airborne dust. The microbes were real, and they traveled through the air. Still, his germ theory was too radical for many, but it inspired others. In Scotland, Joseph Lister began sterilizing surgical instruments with carbolic acid. Suddenly, his patients stopped dying from infections. In Germany, Robert Koch used Pasteur's methods to identify the bacteria responsible for anthrax and tuberculosis. The tide turned. What had been dismissed as fantasy became the foundation of modern medicine. Pasteur's work gave rise to sterilization, pasteurization, and vaccines for rabies and anthrax. Hospitals transformed from houses of death to sanctuaries of healing, and the world saw for the first time the invisible war happening within every wound, every cough, every drop of water. It's easy now to forget how controversial the idea once was, how long people clung to older explanations, how deeply pride and tradition resisted the invisible truth. Pasteur's story reminds us that progress often hides in overlooked corners, that the smallest things, organisms too tiny to see, can change the course of human history. And that true discovery sometimes begins not with a cure, but with a question no one else thinks to ask. So we're left with this reflection. In today's world of information overload, what invisible truths are still being ignored? Not because we lack evidence, but because we've already decided what's real. For centuries, the sky was considered perfect, silent, orderly, and eternal. The stars were fixed. The planets moved in graceful arcs. And the heavens, unlike the chaotic earth, were pure. So when villagers claimed that rocks fell from the sky, the scientific world rolled its eyes. It was superstition, they said. Folklore, a remnant of primitive belief. Learned societies dismissed the idea with absolute certainty. Rocks could not fall from nowhere. The very suggestion violated the rational universe they had come to believe in. When a meteorite reportedly struck Connecticut, even President Thomas Jefferson quipped that it was more likely for Yankee professors to lie than for stones to fall from heaven. But the sky did fall, and it chose an audience too large to ignore. On a spring day in 1803, the town of L'Aigle in France was startled by a booming explosion. Witnesses described a fireball streaking across the sky, followed by a rain of over 3,000 stones. It wasn't a single anecdote, it was a public event. The ground was littered with charred fragments. The spectacle was undeniable. The French Academy of Sciences dispatched a young physicist, Jean-Baptiste Biot, to investigate. His meticulous report confirmed the impossible. The stones had indeed fallen from the sky. They were real, they were extraterrestrial, and they defied the logic of the Enlightened Age. The ridicule began to falter. Yet even before this celestial event, one man had dared to believe the stories. Ernst Chladni, a German physicist, had studied reports from around the world, eyewitness accounts, physical samples, and recurring details. He compiled them, not as myth, but as evidence. In 1794, he published his theory. These stones came from space. His proposal was ignored, mocked, dismissed. Only after L'Aigle did his work gain the recognition it deserved. The reality was too stark to deny. The heavens were not untouchable. They were dynamic, dangerous, and very much connected to Earth. What had once been the stuff of campfire stories became a new field of science. Today, meteorites are vital clues in understanding the formation of our solar system. Some contain elements older than Earth itself. But the lesson isn't just about astronomy. It's about belief and bias. The scientific world of the Enlightenment prided itself on logic and observation. Yet it ignored direct testimony for over a century because the truth didn't fit the model. So here's the question that remains. How often do we dismiss what we can't explain? Not because it isn't real, but because we're afraid to rewrite the story we already know. The early 20th century held a comforting illusion. The universe was eternal, static, and unchanging. It had always existed and always would. Even Albert Einstein, whose equations hinted otherwise, adjusted his math to preserve this cosmic stillness. A beginning to everything? That sounded like theology, not science. Then came Georges Lemaitre, a Belgian priest and physicist. In the 1920s, he studied Einstein's own equations and dared to follow them to their logical conclusion. The universe was expanding, and if it was expanding, it must have once been compacted into an unimaginably dense, hot origin point. He called it the primeval atom, a day without a yesterday. The idea was too radical. Even Einstein scoffed. Your calculations are correct, but your physics is abominable. The notion of a beginning smacked of creationism. It was philosophical dynamite. The scientific community preferred the steady-state model, the belief that new matter simply appeared as the universe expanded, keeping it eternal and unchanging. Enter Fred Hoyle, an English astronomer and chief advocate of the steady-state theory. During a BBC broadcast in 1949, he mockingly referred to Lemaitre's model as the Big Bang, a dismissive nickname meant to ridicule the idea as simplistic and absurd. The insult stuck. So did the theory. In 1929, Edwin Hubble's observations revealed that galaxies were moving away from us, faster the farther they were. The universe wasn't static. It was expanding, just as Lemaitre had proposed. Then in 1965, a serendipitous discovery sealed the deal. Arno Penzias and Robert Wilson, two radio astronomers, were baffled by a persistent hiss in their antenna. No matter where they pointed it, the signal remained. It turned out to be the faint afterglow of the universe's birth, cosmic microwave background radiation, the echo of the Big Bang. Suddenly, Lemaitre's once laughable theory became the foundation of modern cosmology. The universe had a beginning, and it wasn't myth. It was math, observation, and signal. Today, the Big Bang is not just accepted. It is the starting point for nearly every conversation about the cosmos, but its path to legitimacy was far from smooth. Lemaitre's dual identity, Ceti as a priest and physicist, made many uncomfortable. They feared the merging of science and religion, yet Lemaitre never sought to prove faith through physics. He let the equations speak. And they told of a universe that had once been smaller than a single atom, now stretched across billions of light years. His story reminds us that ideas are often judged not just on their merit, but on their messenger. That truth can arrive in unexpected forms, from voices we are reluctant to hear. So here's the lingering question. When we reject an idea, are we doing so because the evidence is lacking, or because the source makes us uneasy? It began with a poem, a story of gods, war, and a wooden horse. For centuries, Homer's Iliad was treated as literature, not history. A sweeping epic, yes, but fiction. The city of Troy, the rage of Achilles, the fall of a mighty citadel, these were mythic echoes, not archaeological fact. To believe otherwise was to blur the line between fantasy and scholarship. But one man refused to see it that way. Heinrich Schliemann, a wealthy German businessman with no formal training in archaeology, believed the ancient texts were maps in disguise. He wasn't content to read the epics. He wanted to dig them up. In 1871, Schliemann began excavating a mound in northwest Turkey called Hisarlik. The academic world scoffed. He was dismissed as a romantic amateur, a treasure hunter chasing legends. And truthfully, his methods were reckless. He used dynamite to break through layers of earth, destroying valuable historical strata in his race to find Troy. Yet beneath the rubble, he uncovered something astonishing. Not one city, but many, stacked one atop the other, built and rebuilt over thousands of years. In one of the lower layers he found gold and jewelry, which he dramatically declared to be the treasure of Priam, king of Troy. He was wrong about the treasure's identity. It belonged to a much earlier time, but he was right about the site. Later, more careful excavations confirmed that one layer, Troy 7, showed signs of destruction around 1180 BCE, the very era the Trojan War was believed to have taken place. The city in the poem was real. Schliemann's work rewrote history. The boundaries between myth and archaeology blurred. Homer, once confined to literature courses, became a source of historical inquiry. Troy was no longer a symbol. It was a place. Still, Schliemann's legacy is complicated. He unearthed a lost city, yes, but also obliterated parts of it. His passion led to discovery, but also destruction. He was a visionary and a vandal. But perhaps that's the nature of pioneering belief. It is rarely tidy. It pushes past the polite limits of caution and stirs something deeper. The idea that stories, no matter how old or poetic, may carry truths waiting beneath the surface. So we must ask, how many legends do we still dismiss? Not because they're false, but because we've never dared to dig. For as long as humanity has gazed into the cosmos, we've assumed that what we see is all there is. Stars, galaxies, glowing nebulae, the visible universe. But in 1933, a Swiss astrophysicist named Fritz Zwicky looked deeper and saw something profoundly unsettling. The cosmos wasn't adding up. Zwicky was studying the Coma cluster, a dense swarm of galaxies. He calculated its mass in two ways. First, by the light it emitted, and second, by the gravitational pull needed to keep those galaxies from flying apart. The numbers didn't match, not even close. The cluster was moving too fast. Something invisible had to be holding it together. He called it Dunkel Materie, dark matter. An unseen presence hundreds of times more abundant than the stars. It neither emitted nor reflected light, but its gravitational fingerprint was undeniable. The scientific world shrugged. Zwicky was brilliant but abrasive, known for calling colleagues spherical bastards, a reference to being bastards from every angle. His theory was too strange, his personality too difficult, easier to ignore him than accept that most of the universe might be invisible. And so the idea languished in obscurity for decades. Then came Vera Rubin. In the 1970s, Rubin began measuring the rotation curves of spiral galaxies. According to Newtonian physics, stars at the edges should orbit more slowly than those near the center, just as planets farther from the sun move more slowly. But that's not what she found. In galaxy after galaxy, Rubin observed that stars on the outskirts were moving just as fast as those at the core. The only explanation? A massive, invisible halo surrounding each galaxy, dark matter, just as Zwicky had predicted. Rubin's data was meticulous and undeniable. The quiet revolution Zwicky had hinted had finally erupted. Today, dark matter is not fringe, it is foundational. It explains how galaxies form, how they behave, and how the universe is structured on the largest scales. Yet we still don't know what it is. We live in a cosmos where the visible is only a sliver, where the shimmering stars and glowing clouds are just the surface of an unseen ocean. Zwicky and Rubin remind us that sometimes what matters most is what we cannot see. And that truth, no matter how faint, will always leave a gravitational pull. So the question becomes, how much of reality do we still overlook, not because it isn't there, but because we haven't yet learned how to see it? Sometimes the smallest acts carry the greatest consequences. In 1847, a Hungarian doctor named Ignaz Semmelweis noticed something no one else seemed to see, or worse, what others refused to believe. At the Vienna General Hospital, women giving birth under the care of doctors were dying at staggering rates from childbed fever. But in the adjacent clinic, run by midwives, the mortality rate was far lower. Semmelweis searched for answers in every ritual and routine. The beds were the same. The procedures were similar. The only consistent difference, the doctors performed autopsies in the morning, then delivered babies without washing their hands. Then a tragedy struck. A colleague of Semmelweis, a pathologist, died after being pricked during an autopsy. His symptoms mirrored those of the women who died after childbirth. In that moment, Semmelweis saw it. The doctors were unknowingly carrying deadly particles from the dead to the living. He issued a radical order. All medical staff must wash their hands in a chlorinated lime solution before examining patients. The results were immediate and dramatic. Death rates plummeted. The evidence was inarguable. And yet the reaction was not gratitude, it was hostility. Semmelweis's discovery was seen as an affront to the dignity of doctors. How dare he suggest that they, the learned healers, were the source of death? He was mocked, ignored, and eventually dismissed. His career unraveled. He wrote desperate letters accusing his colleagues of murder. His behavior became erratic, his isolation complete. In 1865, he was committed to an asylum. He died there at age 47 from an infected wound, ironically from the very kind of sepsis he had worked to prevent. Years later, his insight was vindicated by Louis Pasteur's germ theory. Today, Semmelweis is known as the savior of mothers, a tragic pioneer whose brilliance was buried by pride. His story is a haunting reminder that truth often meets resistance, not from lack of evidence, but from wounded ego. That innovation can falter, not for being wrong, but for being too early, and so we ask, how many lives are lost, not because we lack the cure, but because we refuse to accept its source? For centuries, the deep forests of Central Africa were drawn in pencil and rumor. The maps called it terra incognita, unknown land. From this blank space came stories of monstrous apes, creatures taller than men, with immense strength and strange human-like features. Sailors and explorers described them in hushed tones. But the scientific world scoffed. The idea of undiscovered large primates living in the 19th century sounded absurd. Zoology was entering its golden age. Everything had a name, a genus, a classification. Something as massive and distinctive as a gorilla could not simply exist unstudied. So the tales were chalked up to myth, perhaps exaggerated baboons, perhaps fantasies. Then came Thomas Savage, an American missionary and physician working in Liberia. He listened to the local people, not as a conqueror or a collector, but as a student. He was shown skulls, thick-boned, unfamiliar, and clearly not from any known ape. Teaming up with Harvard anatomist Jeffries Wyman, Savage published a paper in 1847 describing a new species, troglodytes gorilla. Skepticism remained. Bones were one thing, but where was the living creature? A decade later, explorer Paul du Chaillu entered the equatorial rainforests with a mission to find the truth. What he returned with shocked the world. Preserved gorilla skins and skeletons, physical proof of the animal behind the stories. London's scientific community erupted. Some hailed du Chaillu as a hero. Others called him a liar. The gorilla, now unmistakably real, upended the neat hierarchy of zoology. It wasn't just that the beast existed. It was how human it looked, how closely it mirrored us. The discovery arrived at a volatile moment. Darwin's On the Origin of Species had just been published. The idea of evolution was trembling on the edge of acceptance. And here was a massive, intelligent ape hidden in the forests of Africa, blurring the line between man and beast. Today, the gorilla is iconic, a symbol of conservation, intelligence, and endangered beauty. But its entrance into science was not smooth. It had to fight its way out of myth through prejudice and fear. This story reminds us that sometimes the world is more mysterious than we allow, that even in an age of reason, the unfamiliar can be dismissed not because it's implausible, but because it unsettles our sense of control. So we must ask, what truths still wait in the shadows of our certainty, ignored not because they are invisible, but because we are unwilling to see them? It began with a mystery that defied biology's most basic rule. For generations, scientists believed that all infectious agents must contain genetic material, DNA or RNA. Without it, replication was impossible. Viruses, bacteria, parasites, fungi, they all followed this law. It was fundamental. And then came diseases like scrapie in sheep, mad cow disease in cattle, and Creutzfeldt-Jakob disease in humans, neurodegenerative illnesses that were clearly contagious, yet left no trace of a conventional pathogen. Brains riddled with holes like sponges. Death inevitable. But no bacteria, no virus, nothing to explain the spread. In 1982, Stanley Prusiner, a neurologist at the University of California, proposed an answer so radical it bordered on heresy. The infectious agent was not a living organism at all. It was a protein. A simple protein, misfolded into a deadly shape, could trigger a chain reaction, corrupting normal proteins around it, warping their form, and destroying brain tissue. He called it a prion, a proteinaceous infectious particle. The reaction was swift and brutal. The idea was mocked, the logic ridiculed. How could something without a genetic code copy itself? It defied the central dogma of biology. Prusiner was labeled a crank, his papers rejected, his funding slashed. He pressed on. With painstaking precision, Prusiner and his team isolated the agent from infected brain tissue. They demonstrated that mice without the gene for the normal version of the protein were immune. The evidence piled up. Then, in the 1990s, the world changed. An outbreak of mad cow disease swept through Britain. People began falling ill. The disease jumped the species barrier. And suddenly, the impossible theory was the only one that made sense. In 1997, Stanley Prusiner was awarded the Nobel Prize in Physiology or Medicine. The idea, once dismissed as absurd, became a cornerstone of modern neurobiology. Prions remain some of the most mysterious entities in science. They challenge our definitions of life, of replication, of disease itself. They are not alive, yet they spread. They carry no genes, yet they inherit shape. Prusiner's journey is a testament to the importance of defiance in science, not defiance for its own sake, but the courage to question the rules when the evidence demands it. So we ask again, what other boundaries have we drawn too firmly? What other definitions of life, of intelligence, of risk might crumble under the weight of one persistent idea? Sometimes the ridicule isn't about the theory, it's about the person delivering it. And sometimes the idea is so strange, so unsettling, that it seems to belong to fiction. That was the case with Alfred Wegener's drifting continents, with Louis Pasteur's invisible germs. And again with a man named Georges Lemaitre, who dared to suggest the universe had a beginning. But before all of them came a priest named Claudius Ptolemy, whose vision of a geocentric cosmos held sway for over a millennium. And long after him came modern voices who would whisper of other, less tangible mysteries. Among them was a different kind of wanderer, one who saw patterns in the silence between the stars. By the 20th century, we believed we understood the structure of the cosmos. It was vast, yes, but also measurable, predictable, complete. But the deeper astronomers looked into space, the more something seemed off. Galaxies didn't move the way they should. Their rotations defied gravity. The visible matter, the stars and dust, wasn't enough to account for their behavior. Fritz Zwicky had raised this alarm in the 1930s, coining the term dark matter. But even decades later, the idea remained murky, theoretical. Then came Vera Rubin. Quiet, meticulous, relentless. Her studies of spiral galaxies revealed that their outer edges spun just as fast as their centers, an impossibility without some invisible mass holding them together. Dark matter, once dismissed, became essential. And yet even that wasn't the end of the mystery, because as scientists refined their models, another discrepancy emerged. Not only was there unseen mass, there was something even stranger, unseen energy. Galaxies weren't just coasting apart, they were accelerating away from each other. The universe was expanding faster and faster, pushed by something no one could identify. They called it dark energy. Together, dark matter and dark energy make up 95% of the universe. Everything we can see, all the stars, planets, galaxies, accounts for less than 5%. The rest is invisible, unknown, and only inferred by its effects. We now know that we are living in a universe that is mostly not what we think it is. So much of science is built on what we can measure. But what if the future of discovery lies not in what's visible, but in what's missing? And so we pause here, on the edge of our understanding, and ask, what happens when the greatest truths are not in the light, but in the dark? In the arc of scientific history, ridicule often marks the beginning of a revolution. But sometimes the revolution is quiet. It begins not in a laboratory or lecture hall, but in the calm, persistent doubt of someone who sees what others overlook. The story of the prion, the infectious protein, challenged the very structure of biology. But what it left in its wake was something larger, a reminder that certainty can be the enemy of discovery. Stanley Prusiner wasn't looking for praise. He was chasing an explanation for a class of diseases that defied every rule. His idea, once dismissed as absurd, reshaped medicine. It showed us that replication, heredity, and infection could happen without genes, that biology had not yet written its final chapter. The pattern is familiar now. An idea arises. It is mocked, dismissed, even condemned. But it persists, it gathers evidence, and in time it becomes the very foundation of a new way of thinking. From Wegener's drifting continents to Pasteur's invisible enemies. From Copernicus and Galileo's displaced Earth to Lemaitre's expanding universe. From falling stones once called fantasy to the dark matter and energy that now define our cosmos. Over and over, the arc bends toward understanding, but not without resistance. What unites these stories is not just the truth they reveal. It is the courage required to speak them. Each figure stood often alone in defiance of consensus. They bore the weight of mockery, isolation, and in some cases, madness. But their ideas endured. We are reminded that science is not a fixed body of knowledge. It is a living, breathing process. It thrives on questions that challenge, on data that discomforts, on voices that refuse to stay silent. And so, as we approach the end of this journey, one final idea rises from the quiet, that the most powerful force in science is not certainty. It is humility, the willingness to ask again, to look again, to be wrong, and to try anyway. We end this chapter not with an answer, but with an invitation. What truth, ignored today, mocked, or feared, might one day define the world we leave behind? What unites all these stories, from drifting continents to invisible microbes, from sky stones to the echo of creation, isn't just the science. It's the human struggle that surrounds it. Behind every dismissed theory is someone who asked a question others weren't ready to face. And behind every eventual truth is a trail of resistance, laughter, and loss. We like to think of knowledge as a ladder we steadily climb, but it's more like a winding path interrupted by thickets of doubt, detours of pride, and sudden openings into light. Each breakthrough came not because consensus welcomed it, but because someone insisted on seeing clearly when it was easier to look away. The scientist standing alone with an idea is a timeless image. Sometimes they are silenced. Sometimes they are broken. Sometimes they are vindicated only after death. But always their questions echo forward. Their courage becomes the soil from which new understanding grows. It's tempting to believe that we now live in an age beyond ridicule, that science is open-minded, that truth rises quickly to the top. But the lessons of history suggest otherwise. Every generation has its blind spots, its untouchable assumptions, its professional orthodoxies. And every generation needs its question askers, its patient observers, its stubborn believers. Perhaps this is the real message behind these once ridiculed ideas. Not that science triumphs, but that curiosity endures. That truth does not need to shout. It needs only to be noticed, tested, and held, even when it costs something to do so. So we end not with finality, but with a mirror. What ideas are we dismissing today? Which voices are we too quick to laugh at? And in the centuries to come, what forgotten notebook, overlooked experiment, or silenced insight might become the cornerstone of a world we have not yet imagined? The story of discovery is not just about what we learn. It's about how willing we are to keep learning, especially when the truth feels impossible.